Okay. So in this last lectures, we have been talking about the relationship between strain and polarization, but we have done it in a very, very particular case, which is that in our model crystal, we have been thinking about polarization only along the vertical direction, proportional to how much the central cation moves along the vertical, and we have been talking about strain also along the vertical direction. Okay? All right. Now, for practical purposes, it's very, very important to understand how the polarization reacts when the strain is applied not along the vertical but in the horizontal plane, because this is the geometry that we have in thin films of ferroelectric that are grown on a substrate, where the substrate imposes its lattice constant to some extent. Okay, so what we are going to do is to generalize many of our arguments to the case in which our order parameters are two-dimensional. So instead, before we were really working with a uniaxial case, which is enough to introduce most of the basic concepts. Now we are going to talk about a biaxial case where the polarization can be in the vertical but also in the horizontal. Okay? And with this generalization, 3D is really very trivial. I mean, the main ideas you are going to see here. All right. So from now on, the state of our crystal is still very simple. Is going to be described by not only two numbers, but four numbers. We are going to have Px and Py, and Px and Py are going to quantify essentially how the central atom moves from the center, huh? in a very simple and intuitive way. We will say that how much it displaces horizontally will be Px, how much it displaces vertically will be Py, essentially, right? So this is a charged cation, it creates a dipole, polarization is dipole per unit volume, so these things are clearly related. And of course, we can displace horizontally and vertically in either positive or negative, in the positive or negative sense. All right, and for the strains, let me draw them in red. So we have, let's do it like this. We are going to call this guy eta 1 and this guy eta 2. Okay. Using numbers is very typical for strains in something called void notation, so we are going to adopt it here. So direction 1 is going to be direction x, direction 2, direction y, but for the strains we are going to use eta 1 and eta 2. Okay? All right, so now we have four numbers. And this one is asking us to retire it. All right. So in a situation like this, well, let's go by parts. What do we want? We need to generalize quite a few things as compared to what we have done so far, right? The first thing we need is to write a Landau potential that now depends on Px, Py, eta 1, and eta 2. Okay? So let's just proceed, let's say, systematically. So we want to write f of Px, Py, eta 1, eta 2, that depends also on temperature and eventually on the applied electric field, which would also have two components, electric field along x and along y. Let's not worry about that one for the moment. This Landau potential sounds terribly complicated in principle, but let's split it in parts. Let's do one that has to do with the polarization. Well, let me use this notation, Px, Py. A part that is purely elastic, that depends on eta 1 and eta 2, and a part that accounts for the interaction between polarizations and strain, right? So I don't even write the dependence. That one depends on everything. So we have some work to do here. As you remember, in the uniaxial case, we argued from symmetry that this potential, when when we were only considering Py, was very simple. But now, in principle, this can be more complicated, right? So, in principle, we have to think it through again. If I simply plot or write down the possible terms in this potential, let me just do it. So, f of px, py, in principle, could have terms that are proportional to the polarizations linearly. So, you could have terms that are proportional to px, to py. Let me write it like this, using a very loose mathematical notation. I could have terms that are proportional to harmonic terms that I can form with these two variables. So I could have things that are proportional to px squared, py squared, and the cross product between px and py. I could have terms that are go like the cube. So you can imagine px cube, py cube, px squared, py, dot, dot, dot. And following, for the moment, trying to mimic what we had before, or trying to have a more general theory where, of course, if I write a more general theory and I say that px is equal to 0 and eta 1 equal to 0, I have to recover the previous theory. So let me go up to fourth order, right? This is a necessary condition to recover our previous simpler theory. So to fourth order, we could have terms that are proportional to this, or coupling terms in our energy. And then we could have things that are like this. And then we could have things that are like this. And a few others. Okay, so this exercise of ultimately looking at what happens in a thin film, and therefore a biaxial ferroelectric, forces us to introduce kind of a more systematic way to deal with symmetry. Okay, because we want to see which of these terms actually are allowed in our potential. Okay? So that's what we are going to do. Okay, let me clean a little bit now that we have defined our variables. Well, clean is a way of speaking. Okay, let's just for a moment think about which are the symmetries that we have to worry about. I have a system, a crystal, which in the state where the polarization is 0 and all the strains are 0, all the strains, let me write them like this, are 0. In this state, this crystal has a unit cell that is a perfect square, okay? And it has all the symmetries that you would expect in a square. Okay? So without being very systematic about this, but at the very least, we can certainly anticipate that there are certain obvious symmetries, right? There is a mirror plane here. So if I add with this mirror plane, these atoms go here, these atoms go there, nothing changes, this is fine, right? So this mirror plane, we are going to call it sigma y, because it's the mirror plane perpendicular to the direction y. What else? There is another mirror plane here. We've never worried about this one before, but now that the polarization can have an x component, we need to worry. So obviously, that mirror plane would take these atoms here, these atoms there. This guy we call sigma x. Okay? This mirror plane also means that if this atom goes out in this direction, the energy changes, but the energy of the state where this atom goes here has to be the same as the energy of the state when that atom goes there. Right? So these are the symmetries we expect, and the symmetry operation is that sigma x. And finally, the most critical in a sense operation is one that connects x with y. Okay, so there are several of those. One that is very obvious, blue, is a fourfold axis about this axis that comes out of the whiteboard, right? So if I put myself here and I rotate by 90 degrees, this atom goes here, this atom goes here, this one goes here, nothing changes. So that is another symmetry operation that we expect, and we are going to call this one C for set plus, where set is the direction that we are not plotting, and 4 refers to this one being a 4-4 axis, meaning that we have to apply it 4 times to recover exactly the same thing as we started. Okay? Because 90 times 4 is 360. All right. Now, what do we expect? Imagine, let's start only with the polarization. Imagine we start with an arbitrary state, where for px and py, we give 2 specific values, x and y. Okay? It means that my central atom has moved by an amount x in the x direction. X can be positive or negative, and it has moved by an amount y in the vertical direction. Y can be positive or negative. Okay? Okay. Now we are going to work out a little table that tells us, so I want to imagine that I apply symmetry operations to this general state where px equals to x and py equals to y. Okay? And I want to see what the transformed state looks like. Let's start with the planes that are very simple. So here I'm going to write the symmetry operation. So sigma x, for example. So sigma x is the plane that intersects the whiteboard along this vertical line, right? And it's pretty clear that if my atom has an x component, so it has moved off center, and there is an x component describing that motion, meaning that you project over the x-axis, and that's different from 0. If I apply sigma x, that x component will change its sign. Okay, so if the atom was here, I apply sigma x, the atom goes here. So I go from px being to x to px being minus x. Okay, the transformed state has a polarization along x that is exactly the same but with a different sign, right? On the other hand, if the off-centering has a y component and I apply that mirror plane, well, since that atom would be sitting in the plane, it's transformed into itself, and the y component doesn't change. Okay? So this is telling us something very interesting. If I have a state where px and py equal xy, that state has to have the same energy as another state where px, py equal minus xy. In a second, we see which one of these terms survive this kind of condition. But let's look for other conditions. This is simply one condition, of course. We can look at sigma y. What does sigma y do? Well, this one is trivial enough, right? Sigma y is this mirror plane, so any x component will be left as it is, and any y motion or motion along the vertical will be reversed. Quite trivial, right? And finally, if I have this fourfold axis of complicated notation, what am I getting? So imagine I have an atom that has an x component. Okay, so it is there, the atom is there, right? If I apply now my fourfold axis, the atom will change position and it will go here. So it will have a y component that equals my former x component, right? So in my new state, py is equal to the initial x with the same sign. Sign is important here. Now imagine I start with a y displacement. Okay, so I start with an atom here, and I transform by the fourfold axis that takes this guy over there. So in the new state, I have an x component that equals to my initial y, but changing the sign. So my new state has a px equal to minus 1. Simple enough, right? Now, as I said, we could call these guys, by the way, we can say that this is the state transformed by the identity operation. And of course, you could tell me, but is this all we need to consider? Yeah, I think this is probably all we need to consider for this very simple system. Okay, we could apply a second fourfold axis, for example, that would take this. So if x was going here like x, here minus y will go here to minus y. If y was going here to minus y, now x will go here to minus x. This is if I apply the fourfold axis 2 times. This guy will be transformed into this. Okay? But you see, the application of 2 times this fourfold axis is like the application of this plane and then this plane. So in this very simple system, these 3 operations are probably enough to get everything we need. Okay? This we would call more technically generators, because their application gives us all the possible symmetry transformations. Okay? It's always possible to find a set of symmetry operations that generate all the rest, and therefore considering those is enough. Okay. All right, but now the key thing is that states 1, 2, 3, and 4 here have to have the same energy. So we can just evaluate the same energy. Right? So for example, if these guys have to have the same energy, and we express the energy as a linear combination of terms that are proportional to this kind of powers of the 2 components, it means that power by power, our energy has to respect this symmetry. Okay? So a symmetry operation will never mix px with px to the cube. So it has to be true that at this level we respect the symmetry, at this level we respect the symmetry, etc., etc. Okay, so let's see how it works. Let's imagine, for example, that we have at the linear level our energy, let me call it F1 for the P, okay? Loose notation, 1 means that these are linear, okay? But let me imagine that I can give this a general form, alpha px plus beta py, right? These are 2 parameters. And the question I am asking is whether these parameters can be different from 0, and so that we still respect the symmetries that we expect to respect. Okay? Now the energy, let's number these states, number 1, number 2, number 3, number 4. Probably this is a clever thing to do. So the energy of this thing for state number 1 is simply alpha x plus beta y. Okay? Quite clear. The energy given by this term, these linear terms for state number 2 is minus alpha x plus beta y. Okay? For state number 3, the energy given by these terms would be alpha x minus beta y, and for state number 4, it would be minus alpha y plus beta x. Simple enough? Now, and symmetry requires that these 4 energies are the same for any arbitrary choice of x and y. So, since these 2, for example, have to be the same for any x and y, well, this part is trivial, but for these 2 to be the same for any x, the only possibility is that alpha equal to 0, right? Similarly, if these 2 guys, number 1 and number 3, have to have the same energy for arbitrary x and y, well, for x is trivial, but for y, the only possibility is that beta equals to 0. And we are done. So essentially, we did this in a very hand-wavy manner in the very first lecture or the second lecture, I don't remember. Okay, but here you see it in a more systematic manner. We can generate collections of states that have to have the same energy. Then we see what that means. It means that these 2 parameters in particular are 0. Okay? So let me just erase them. And I guess you will be easily convinced that since I have symmetries that I can use to change the sign of individual components, that means that any odd power of an individual component is gone. Okay, so it means that, for example, this guy cannot exist. Okay, none of these guys can exist. There is always an odd power. And over here, for example, this guy cannot exist, etc., etc. All right? Very good. Now let's pay a bit of attention to the quadratic terms, right? I mean, one of them is gone, but we still could write another subterm of the energy. Let's call it F super 2 of P. And we are going to stick to alpha and beta. And now the two candidates that we have to give us something are px squared and py squared. So let me write it simply. All right? And now, of course, we are going to see what this gives us as a contribution to the energy for our four very well chosen states that test essentially the complete symmetry of the system. What do I have? For state number 1, this gives us a contribution that goes like this. I am just substituting px equals to x, py equals to y. For state number 2, I have something that, well, I have changed one sign, but everything is a square. So state number 2 says something like that. State number 3 is similarly trivial. And state number 4 is a bit less trivial because here I have swapped x and y. There is also a change of sign, but that doesn't matter because there is a square. So I get something like alpha y squared plus beta x squared. And all these guys have to be the same for arbitrary choice of y and x. So of course, the first three don't give us much information because they are obviously the same. But if I compare this one to this one, and this has to be the same for any x and any y, it's pretty clear that yes, this can happen, but only if alpha equals beta. All right? So when we have this, it means that at this level, in the expansion, these two terms can appear, but they can only appear in a very specific combination. They have to have the same parameters in front, which means that they can only appear as the addition. And then with the parameter multiplying that addition. Okay? By doing this, what we have figured out is a symmetry invariant. We have two variables at quadratic order here that can appear only in this particular combination, px squared plus py squared. Anything else is not allowed. Okay? It means that the parameter in front of those is the same, which of course makes a lot of sense. The energetics of my polarization, if this atom moves up, has to be the same as if it moves to the right or to the left. Right? So we are recovering, of course, the symmetry imposed by the fourfold axis, which is the one that gave us this condition in our little table. So polarizing vertical positive is the same as polarizing to the left or to the right. Cool, right? All right. Now let's go to fourth order. And to the third order, we had already figured out that everything goes. To the fourth order, what do we have here? We have, again, let's do it. Well, some of it is should already be kind of obvious, but let's do the whole thing, since it is not too late. So in principle, what can I have here? I can have a term like this, px to the fourth, py to the fourth, but now I have more, right? At the very least, I have this guy, gamma px to the square, py square. And then that's really all there is, because any other combination will involve some odd power, which we know cannot happen. And here you really don't have to be a genius to know where we are going. The first evaluation of the energy is simply alpha x to the fourth, beta y to the fourth, gamma x squared y squared. Here the main difficulty is going to be able to write the whiteboard. Quite obviously, states number 2 and number 3 don't add any information because all they do is to change signs. Because the powers are even, we are vaccinated against that. But when we swap, here we have some extra information, right? And again, there is a change of sign, but that doesn't come about anywhere. What happens is that I get alpha y to the fourth plus beta x to the fourth plus gamma x squared y squared. All right, sounds reasonable. So, if these two energies have to be the same for arbitrary choices of x and y, well, on gamma there is absolutely no condition. So we haven't been able to kill gamma. It means that by symmetry, it doesn't need to be zero. That means that it will not be zero, except for, accidental cancellation in some funny system. Gamma is allowed, and it is allowed like this, simply the product of px squared, py squared. That is an invariant. Okay? Okay, gamma, okay. And these two, we have a similar situation as before, right? Essentially, these two can give us the same energy for arbitrary choices of y and x and y, sorry, as long as alpha and beta are the same number. So if we think about the invariants to fourth order, what do we have? We have the addition of these two guys and this guy by itself. So two invariants. Not very difficult, right? Of course, by the way, mathematically, if you go to the theory of discrete symmetry groups, there are much more elegant ways to derive these invariants using irreducible representations and related results. But ultimately, it boils down to this brute force method should always do the job, ultimately. And you can see the symmetry in action. All right, so now we can already write our energy for the polarization. So let me remove. So f of px py is going to look like 1 over 2, something I'm going to keep calling alpha prime minus t minus tc, but then now this guy is going to be multiplying px squared py squared. Then I have to have another invariant that I can call 1 over 4, sorry, beta px to the fourth, py to the fourth. And finally, let me introduce 1 over 2 gamma px squared py squared. Okay. If you compare it with what we had before, by the way, I have already kind of hypothesized that this will be the only temperature-dependent parameter that will give us a continuous phase transition, as we did before. Okay. Obviously, we never worried about this, but if the polarization could be up or down, it could also be left or right in principle. Okay, so it makes good sense to keep that, and then we have a fourth order term that essentially defines our minima, and here we have a funny coupling that we are going to talk in a moment. Okay, okay, so let's spend a bit of time with this one. And maybe we will call it for this video. Okay, so three terms. Definitely in the limit that px equals to 0, this is the term we used to have before, and this is the term we used to have before, clearly, right? Now, there is a funny situation here that is worth considering. This is a way of writing the Landau potential that you will find in many references, but which I personally don't like at all. So I would like to propose right now a different way to write it that we also reduce to what we are used to in the case of only a uniaxial ferroelectric, but which has certain advantages. So imagine let's stay with this term, okay? Let's stay with the fourth order part, what we have called F4. F4 of P. So what if I construct the following invariants? I'm going to write an invariant like I have here, but then I want to write an invariant that is like this. Okay? There is a good reason to do this. You will see it in a moment. This stuff has to be an invariant because we know that the sum of px squared py squared is totally invariant by all the symmetry elements, so it doesn't change. So if this one doesn't change, if I square it, it will not change either. So that is an invariant. So if what is in the parentheses is invariant, if I square it, it's also going to be invariant. It doesn't change under the symmetry operation, right? So what am I doing here? Do I have a new invariant? The answer is no. Let's imagine for a second that I write, I say that this guy is beta, just for, let me call this, if I work with these invariants, let me hypothesize sign coefficients here that are going to be beta bar and alpha and gamma bar, okay? Now, one thing I can do is to expand this, okay? So I have something like 1, 4, beta bar, and then what do I have? I have px to the 4, py to the 4 on one side, but I have something extra, right? I have 2 times, so 1 over 2 beta bar, px squared, py squared, okay? And over here, I have 1 over 2 gamma bar px squared, py squared. Okay? By simply expanding that. Quite clear, right? And now we realize that by expanding this, I have recovered something that looks like the invariant I have naturally derived before, plus the other invariant. So I can rewrite the whole thing as 1 over 4 beta bar px to the 4, sorry, py to the 4th, plus 1 over 2 beta bar plus gamma bar px squared py squared. So the number of invariants in this model, in this system, to fourth order is only 2. We can write them like this, or we can write them like this, but we have only 2, meaning that we only have 2 independent parameters that describe our energy. Then we can choose, but once we have invariants, we can choose as an invariant any arbitrary linear combination of them. Makes good sense. And that's what we are doing. Okay? The descriptions are totally equivalent, and here we have explicitly the correspondence. So this energy expressed with beta and gamma will be the same as this energy expressed with beta bar and gamma bar, as long as beta bar equals to beta and gamma equals beta bar plus gamma bar. Okay? So this has the same form as that, and it will be the same as long as this parameter equals to that parameter and the sum of these two equals to that. Okay? So the freedom I have to choose parameters is exactly the same. I have 2 independent parameters that describe my energy surface at the fourth order. But then, of course, depending on which linear combination I choose, they can look like something or something else. But everything is equivalent. All right. And now, why do I prefer this representation? I prefer this representation. I strongly encourage to use this representation because in this representation here we have the modulus of the polarization to the fourth, essentially. Okay? And if you think about the energy landscape, this term is perfectly isotropic. Okay? So if we went to polar coordinates, for example, this term, so if we represent this guy as some p and then the cosine of some theta, right? Then py as p sine of theta. If we went to polar coordinates, this guy is p to the fourth. It doesn't depend on the angle. So we have an isotropic part of the energy, and all the anisotropy is captured here. So in this representation, gamma bar gives us the anisotropy. In the other representation, the anisotropy is distributed between the two parameters. And this is a very useful thing to separate. To work as much as possible with isotropic contributions to the energy and anisotropic contributions to the energy. And why is this relevant? And with this point I finish. Because we haven't worried about this yet, but in our very simple and boring looking crystal, well, if the atom can only move up and down, it's boring. There is only one direction. But if it can also move left or right, there is not obvious any longer whether the lowest energy of this crystal looks like this, with the atom moving along one of the Cartesian directions, let's say, or maybe it looks like this, with the atom moving along one diagonal. Okay? So from what you know, probably you are familiar with perovskite oxides. Some of them have tetragonal faces, rhombohedral faces, or rhombic faces. That essentially is reflecting the anisotropy that in different systems will make this atom prefer to go along the Cartesian or pseudo-cubic direction, and in others will push it to go rather along a diagonal. And in this representation, in this clever representation that I am going to actually, let me remove the one that we got by default and substitute by the one I prefer, and which we will use systematically. In this clever representation, so I'm going to redefine the coupling constants, okay? Now I have 1/4 beta, but now this beta is multiplying to px squared, py squared, and now I have 1/2 gamma, and now this gamma multiplies to px squared, py squared. Okay. In this representation, these two terms are isotropic. They don't distinguish direction. So the term that tells me if the system wants to have only one component of the polarization different from zero, or the two components simultaneously different from zero, is gamma. And what tells me that? The sign of this parameter. So automatically, if gamma is positive, it means that if both components are different from zero, the energy goes up. Therefore, the lowest energy solution is when only one component is different from zero. Okay? So if gamma is positive, that automatically means that the ground state of the system looks something like this, P0. Plus minus P, the P can be in X, can be in Y. I have 4 like this, but it looks like that. If that parameter is negative, on the other hand, the ground state of the system is going to look like this, P. And we know that immediately from the sign of gamma. And this is going to be very interesting and important soon enough when we look at, for example, a biaxial strain, and how a strain actually can allow us to make the polarization rotate from being out of the plane to the plane. Okay, let's leave it like this right now. In the next episode, we will talk about the strain. We will do the same symmetry analysis for the strain, for the coupling term, and then eventually we would make it to the epitaxial thin films. Questions?